Hello. Today we're going to talk about sort of defining what harmful algal blooms are, and then we will use a case study from Western Lake Erie and the Toledo water system to look a little bit more in depth on the technology around. So we'll start with what is a harmful algal bloom and a definition. We'll look at what some of the contributing factors for causing a HAB or the initiation of a HAB is. We'll look at the greatest unknown of all about the HABs, which is what triggers a bloom. Then we'll briefly touch on sampling strategies, autonomous systems versus discrete sampling, and some of the water quality and nutrient sensors that are available to use to do continuous monitoring, specifically phytoplankton fluorescence and the nutrient sensors. Okay, so defining a HAB, a harmful algal bloom, is not as easy as one might think. This is a paper that was published in the Journal of Great Lakes Research a couple of years ago. It actually deals with the 2014 situation in Western Erie. But what's really cool about this paper is that they really go into depth in the introduction on just exactly what a HAB is and the different matrices and considerations that go into effect about calling something a harmful algal bloom. This is really a non-trivial point because societally we spend a lot of time and effort tracking harmful algal blooms and coming up with mitigating strategies. So if you don't really know what you're calling a harmful algal bloom, you can go off base on both acknowledging or not acknowledging a current situation, and then actually tracking what works for mitigation purposes. So it's an important consideration, even though it seems somewhat at the start. So in that, we're going to go to a little bit more in depth of just exactly what that is. I will say that this is sort of my overview. There's a huge number of researchers working in the HAB space. You're getting my sort of high-level viewpoint of the world. That's not by any means the way I organize my thoughts, and there are certainly other people who have much more expertise on a lot of any individual parts of what we're going to be presenting this week and next. And I'll hopefully refer you to their research, and when we're done here, we will be putting up these presentations, and we will add links to further research and websites, et cetera. Okay, so a harmful algal bloom. Well, it certainly has to be harmful, and it has to be algal, and it has to be a bloom. Algal means that it's a plant material, autotrophic production. Plants move along and grow on the basis of three different things: sunlight, nutrients, and time. You need sunlight as a source for photosynthesis. You need the nutrients to build the structures of the cell, and you need time in an environment in which the nutrients and the sunlight are replete enough to have net phytoplankton growth. So that's sort of what, and no surprise, that's the basis of the entire worldwide economy is plants and autotrophic production. The question with harmful algal blooms, of course, is when this becomes a runaway situation. So for blooms, and that's our runaway, blooms are, in this context, a high concentration of plants. For the most part, this means that a single species dominates a bloom, and the inverse of that is, of course, that there's minimal diversity. Minimal diversity in a single species means that blooms are both episodic and unstable. Surprisingly, blooms occur as a response to conditions in which there's generally a rapid change in the environment or a new environment to exploit. So, within the water systems, that's a new basin or a big overturn event, something that's changed the conditions that moved away from what had been a somewhat stable or at least oscillating autotrophic heterotrophic system, which the autotrophs is a single autotroph single plant species starts to dominate the entire environment. So blooms are an endless phenomenon. They occur in pretty much any type of an environment in which there's a doubling or a increase in concentration of a particular substance or the value of a particular substance, in which there's a limitation, and the ongoing valuation or concentration of that substance is dependent on the previous substance. So for plants, that's simply a function that unicellular plants grow by dividing. So at every stage of their vegetative growth, the number of plants at some time post the start of the experiment or the start of the situation or the start of or the time zero that you appeared at the environment, there's going to be twice as many cells, and then twice as many cells and twice as many cells. And the graphs over here on the right are two exponential curves just taken from a doubling sequence. And you'll note that the top curve and the bottom curve look pretty much exactly the same. The only difference is the scale, and that's sort of a function of an exponential curve. As you depending on what time you move through that, the curve in fact looks exactly the same. It's just that the trail off to the left, the small numbers that grow into the large numbers become essentially just shift along. So you can explode an exponential growth curve at any point, and it'll look the same. So for a bloom consideration for phytoplankton, what it really means is, what do you define? And the plants will be doubling at some clockwork, depending on their energy and nutrient uptake kinetics. And then it's just a question of whether that becomes high enough to cause it to bloom. So for the most part, that means that the things that cause blooms have shorter doubling times and tend to outrun their competitors, so that when we observe it as a bloom, they've become a single species that has become the dominant organism within a given environment, and so therefore dominates both the nutrient uptake and the light absorption. That's as if the cells exist within a chemostat and there's only a growth function. Well, in the real world, of course, there's other loss terms. Chiefly, that becomes grazing loss terms or the transfer of energy from the autotrophs into the heterotrophic population. So with that case, you need, to get to a bloom, you need minimal grazing on the species in question, and that can come basically through two different ways. A, you have no grazers, so you're early in the function, and you do not have a heterotrophic population growing up. Or B, you are simply less healing than the other phytoplankton, and so the heterotrophs graze on something other than the species in question, and then you grow up. And then finally, you have we discussed before, is time is one of those things that's important. You have to be in an environment that is conducive to growth, which also means that you have a minimal loss due to infection or settling. Settling here, of course, can be positive or negative. Certainly with a lot of the blue-green algae, they tend to become buoyant in canopy over, and that, of course, is a nice growth strategy for taking out your competitors by simply absorbing the light before they can get to it. That is very apparent in a lot of bloom situations, particularly for the blue-green algae. And then that, of course, interestingly enough, sets up the observance in a remote sensing sense that you can see those blooms very clearly. The problem with that, though, is, of course, you've now biased yourself to when the blooms get to the surface and are apparent in remote sensing. It tends to be late in the stage of the bloom. So it's sort of telling you that you have a bloom after you've already had a bloom. And then in the end, bloom conditions tend to be limited by nutrients with only a certain number of doubling once you get to a high enough concentration. The plants will absorb all the nutrients in a given volume of water, and then will crash. So finally, the hardest part of this, which is defining what harmful means. For the most part, we think of harmful algal blooms, and certainly the ones that get the news are the ones that are toxic, that have paralytic shellfish toxins, have aerosol toxins, are toxins to human or livestock or pets, things that we really don't want to interact with on any basis at any time. And then there's just simply the noxious. They smell, you get a bloom condition, and then at the crash, you get a low oxygen condition, and hypoxia and anoxia leads to fish kills. And it's just, or in a macroalgae sense, or other heterotrophs in which you get jellyfish blooms, you just end up with a mess of water that if you were planning on sailing that day, you're not going to go out. If you're planning on swimming in it, you're not going to go in it, and that, of course, impacts human economies as much as anything else, even if they're not necessarily toxic. In freshwater, the blue-green algae tend to be the biggest one. This is not an exhaustive list, obviously, but microcystis tends to be one of the more important blue-green algae, at least in the United States, growing out. That is the top picture there with the little green cells. They are colonial formers in some cases, but they tend to be a freshwater dominant species. And they are a toxin producer, microcystin, which has a variety of nasty attributes. In saltwater and brackish water, you end up with two of the primary ones. Pseudonychia. Pseudonychia is a cane-forming diatom in which it sometimes expresses domatic acid and sometimes it doesn't. It's been running off the west coast of the United States for quite a while and creating a situation in which the domatic acid is getting into the razor clams and then into the crabbing and shutting down the Dungeness crab season, or at least making it a briefer season. So that certainly has an economic harm, and of course the toxin is not something that we want to be ingesting as we go along. And then there's K. brevis, which I did my PhD work and spent 10 years did my PhD work at Texas A&M and worked in the Gulf of Mexico for many years. And K. brevis is, of course, the primary red tide organism in the Gulf of Mexico and the southeast United States. It's a dinoflagellate and has all sorts of nasty things associated with it. So harmful is something that, in the end, it's really us defining what that is. It's something that we do not want, and we don't want it at a particular place and at a particular time, which means it's really totally a human-made definition. What is a harmful algal bloom is dependent on the beholder, not intrinsic to the bloom itself. And of course, the bloom dynamics are really the question here overall. And if you just think of, well, a large part of the North Atlantic, the spring bloom of diatoms triggers much of the heterotrophic activity that follows on and is an important dynamic in carbon cycling and protein growth, fisheries, et cetera. Well, that's a bloom, but it's certainly not in any way, shape, or form harmful. And yet there's no real distinction between, in terms of the dynamics, between that than a pseudonychia bloom or a microcystis bloom in a more inshore environment, other than it's a bloom that's occurring that has negative impacts to human health and or economic concerns. So that's an interesting way of looking at it, because what that really means is that while we're studying harmful algal blooms, we're really studying bloom and phytoplankton dynamics as a whole. There's really nothing intrinsically unique to studying a harmful algal bloom and understanding what triggers the harmful algal bloom than any other phytoplankton assembly and understanding our natural environment. Okay, so let's look at a particular case, and I love this picture because it really encapsulates a huge range of motions. This is from the Blade, the local newspaper in Toledo, when the mayor was announcing that people could drink water again. So in August of 2014, a large bloom of microcystis occurred right near the intake for Toledo, and they started measuring microcystin in the system, in the water system, and they had to shut it down. So this was, obviously a large economic and societal impact from what had been happening pretty much every year for quite a few years as we went along. So it just so happens that at that time, Scientific were working with other agencies and scientists to look at how continuous data in systems could help predict and monitor. So we sort of hit the jackpot here in that we had a LOBO system, a land-ocean biogeochemical observatory, out in the western Lake Erie and fairly close to the Toledo water input. The goal of the research has been for monitoring prediction. We'll touch on some of the research afterwards in slides. But we certainly knew that contributing factors for this particular bloom was high phosphate loading, particularly from agricultural runoffs through the Maumee River in northwest Ohio. Lake Erie is a very shallow lake. It's one of the larger lakes of the Great Lakes, and yet it's the smaller in volume because it's essentially a big flat pan. I should practice saying that 3 times fast. And the blooms happen in the warm lake summers. So that's the setup, and then the question is well, why do you get a bloom at any particular time and space? So the LOBO system is licensed out of Mabari, the Monterey Bay Aquarium Research Institute, and the idea of the LOBO system is to put together a broad spectrum of physical and biogeochemical sensors, and then build a system in which it calls in and logs the data on a website every half hour. So you get, within half an hour, you get a full spectrum of data from the site that you put the mooring, or in some cases on the dock, et cetera. Lots of different variations you can do. But that allows you to look at essentially current conditions from your desktop. And that gives you a lot of power to look at the system as a whole with a lot less effort and a lot more coverage than going out to sea and sampling. The instruments that we have on them in general is our Suna nitrate sensor, our water quality monitor, which that's a combination of a CTD, salinity, temperature, and pressure. Then we also have optics for chlorophyll fluorescence and backscattering, measured in this case as turbidity. There's also DO sensor on that so we're pretty much hitting the basic suite of biogeochemical and physical sensors that define pretty much parameters of any water body as to the state of the physiology of the water body itself. In the case of the Western Lake Erie, we also had a phosphate sensor, our hydrocycle PO4 sensor. That is a wet chemistry-based sensor that uses molybdate reduction to generate a color. That color is then linearly scaled with creation of soluble reactive phosphate in the water column, and that measurement occurs not relatively continuously, but it's a single measurement over about a 15 to 20 minute time scale. So it matches up with the 30-minute recording and transmission of the data, but it's not, as a wet chemistry measurement, it is limited in time relative to the other measurements, which tend to be on a 1 hertz basis. We'll get into the nuts and bolts of this next week a little bit more. The St. Lucie estuary is home to, I think, 11 LOBOs at the moment, run out of the Florida Atlantic University's Harbor Grant Irlon system. Okay, so with the LOBO system, and we'll go back to look at what we know in terms of the LOBO system and the contributing factors relative to our harmful algal bloom. The high phosphate loading gives us the nutrients. The shallow lake, which means essentially that the phytoplankton is going to be in the photic zone no matter what the conditions are, and also then time in which there's in a warm late summer, you've got decent stratification, and you've basically built up a system in which the phytoplankton are captured in a layer in which there's plenty of nutrients because of the freshwater input from the Maumee River, and you've got plenty of sunlight and not a huge amount of vertical mixing from storms. So it's all set up perfectly, and of course that means that every year you basically get a bloom. Well, yes, you get a bloom every year, but where and when is really sort of the trick to this all. So right in the right-hand box there is LOBO data from the time period that we're talking about, August 2014. The yellow box is the time in which the Toledo turned off their water intake during the crisis. And what we've got there is chlorophyll fluorescence, the phycocyanin fluorescence, and the backscattering turbidity. So chlorophyll fluorescence gives us the total amount of plant material with some caveats based on the physiology of the plants themselves, but it's still a very effective technique to monitor the gross concentration of plant material. The phycocyanin, which is the light-gathering pigment specific to blue-green algae, and is therefore the microcystis uses to trigger itself. So essentially it's a measure of your microcystis concentration in the water. And then backscattering is turbidity. Backscattering is basically a measurement of the light return from particles in the water. So it tends to move with the equivalent spherical diameter of the total equivalent spherical diameter of particles in the water, i.e. the particle mass concentration. So what the black line there gives us is how much total material is in the water column. Now, one of the complications with blue-green algae is where you measure it tends to be very important because blooms go through a phase in which, as they get to a certain concentration, they become buoyant, the colonies rise to the surface, and they canopy over the water column. Well, if all the plant material is in the upper 10 to 20 centimeters, and you put your barometer and backscattering sensor at 1 meter, you can get an apparent disappearance of the bloom when in fact the bloom is going to show up super hot on a remote sensing satellite or airplane-based sensing system. So you have to be cognizant of where you put instrumentation, and of course then vertical structures also play a role in there, and vertical mixing. So if you've set up a canopy situation and then you have an intense front move through and the wind shear on the water column mixes that canopy down again, that can pop up and show up in your sensor, where it's maybe not changing the total concentration in the water column, but it's changed the concentration in front of the sensor. So there's all sorts of complications doing this, and that's one of the problems with a limited data set. You don't eliminate some of those uncertainties. But the trick then is, while it's relatively apparent that we had a bloom situation, you've got a factor of 10 or more in the concentration of phycocyanin and chlorophyll, and you have a very coherent backscatter signal in that yellow box. What you really don't know is why then versus 3 days before, where you also had a high phycocyanin and a high chlorophyll, or any of the smaller blips that you see in the 2 weeks beforehand. So the real question is what triggers a bloom? You've got, especially in areas like the Gulf of Mexico with Cape Brevis and in the Lake Erie with microcystis, there are always spore and seed populations within the water column. It's not a question of presence, absence. It's a question of what stage of the ramp they're on, and are they going to dominate the water column. So I just sort of threw up our little exponential curve there, and I built a quick dampening function. So I have no idea what color that is. It looks gray to me, but I'm colorblind. So, so a bloom condition would be that blue line where you're just sort of going off to infinity. What changes occur in the environment that allow sometimes that exponential to continue on to a bloom, and what causes the group between 12 and 14 that leads to the non-initiation of a bloom. And that's really the scientific goals that a lot of people are working to understanding the predictability of the blooms, and therefore to establish mitigation factors to try to drive the harmful section out of the harmful algal blooms, and just create either an algal bloom that's not harmful, or drop the bloom consideration entirely and not worry about a large-scale variance. So I just sort of highlighted with the arrows some of these previous events that it's very hard to distinguish why you would not have occurred, why you would not have generated an exponential out of those events, or even if you look past the bloom where you had a high phycocyanin concentration a couple of times. Yes, you had still a large amount of microcystis in the environment, but at that time it was not sufficient enough within the intake status to cause a crisis within Toledo. So it was a very specific time period in which there was a very high loading in not just the upper 5 to 10 centimeters or meter of the water, but throughout the water column, so it impacted the water intake. And that's why these things tend to be relatively hard to predict, because there's a lot of unknowns. And we're only looking on this plot with 3 of the measurements that we have from that data system. And of course, there's also remote sensing and all sorts of other data collection methods that were going on at the same time. This is a poster from Tim Davis and some of the other people that we were working with at the time of the 2014 event. Their goal is to drive data collections into predictive models, and they've been working on it for quite a while. And this was a recent poster that documents where they've come. There is a lot of initiation of HAB model development, remote sensing. US EPA is working on that quite a bit. USGS is working on that quite a bit. I'm sure most of the states in which these are happening have their DEQs working on these. So this is perhaps, one might even say, almost oversubscribed in terms of people working on it, but it's a very difficult problem because it really gets down to the root of predicting ecosystems with sparse data sets. And predictive models basically are dependent on data. So the more data we have, the more we can look at the fundamentals of the model and test the model against different data structures. But for the most part, I think the bottom line here is that harmful algal blooms and particular events, while they are predictable in the growth scale, i.e. we know there's going to be a North Atlantic bloom, or we darn well hope that there's going to be a North Atlantic bloom, they're always sensitive to initial conditions. And within the oceanic sphere, which diatom wins out and becomes the bloom species, for the most part, doesn't change the structure of the heterotrophic activity during and after the bloom. It's important for that particular species, but we can predict that it's going to be a diatom bloom overall. Within the harmful algal bloom space, the sensitivity to initial conditions is really, are we going to get the particular species that causes a harmful algal bloom in this environment over these times, i.e. the microcystis, the pseudonychia, the K. brevis, and others, that will cause the harmful algal bloom. And that's a quite a bit different question in which we just simply need more data. So moving to an observational or monitoring or after-the-fact structure of looking at HABs to a predictive structure is inherently going to be dependent on the data, not just the quality of the modeling. They're going to go hand in hand, but you have to have a data source that gets enough data to start knocking down the probabilities that you don't have enough data that you can't predict to make a useful prediction. And I just grabbed one of they make this point in this poster. Just the upper right-hand corner doesn't probably show you too well, but the cycle data sets, I think they actually have these backwards. The bluish diamonds is the cycle data every half hour, and then the grab samples are the grab samples, the ground truthing phosphate. If you look at the variance between them, you'll see that certainly in that middle part of the screen here, where you've undersampled and you're not seeing quite a bit of the variance in the phosphate that you're getting if you look at it every half hour. And this is, of course, true on pretty much every time scale. If you're looking at diel structures, if you're looking at mesoscale structures, if you've set up a sampling scheme in which you are sampling once a day or once a week or once every 2 weeks, you simply aren't going to get the scales of the phenomena that are probably apparent in the data and in the environment and really drive the environment. So in this case, you see the phosphate swinging quite a bit on a daily basis or even on an hourly basis, whereas they're the grab sample data that's collected once a day really misses quite a bit of that. And then, of course, you have sampling bias. If you endlessly get data at noon, and your diel cycle of uptake means that most of the phosphate that's been in the water column or regenerated into the water column or pushed in from the rivers is absorbed by uptake kinetics from the phytoplankton in the morning. You're always going to see an underestimate of the phosphate available to the organisms, and your model will continuously underestimate the amount of growth because your uptake kinetics has sequestered the phosphate out of the dissolved pool and into the particulate pool. That's actually a functional problem with cyclophosphate also, but you just simply grab more samples and you measure the entire 24-hour cycle or the mesoscale cycle, and you can recreate that and you start to see that uptake kinetics. And there's actually a couple of nice papers out early on with phosphate that show that dynamic, which is pretty amazing. So continuous sampling, what it really does is knock out at least some level of sample bias from the structure. There's also just simply the time lag of if you've got a sampling regime that involves you actually going into the field and grabbing that sample. It just takes that much longer to go through that process. And I just sort of wrote down a quick list of steps involved without any time function at all on the right, but there's quite a few steps simply to get a single sample from a grab sample that the effort involved is just huge relative to our own work environment, relative to turning your computer on, going to the website, and seeing the last 24 hours of data on a half-hour basis. And that's just amazingly invaluable. I found it. I'm old enough in this profession now that I started out where we put instruments in the water, and we hoped that we came back a year later and had data in them. And now that we sit there and read from the field from many different sites, from observing systems and monitoring stations, it's a really powerful tool.
Okay, you answer your phone. I'll talk to you later.
So the other thing that you can do with continuous data is you can start to build quality assurance systems built into the data ingestion system, and that allows for a lot quicker throughput of data collection to data utility. The analyzing the data, the interpreting the data, and the reporting the data compresses quite a bit. That's a whole other series of discussions that we could have at some other point that I've been working on for the last few years. But simply the ability to take a bunch of different data continuously over variable time cycles gives us the ability to develop statistical tools that allow us to say, is that instrument operating in the manner that we expected, and therefore can we conclude that the data that we're bringing in is data relative to the phenomena, the target material that we're looking at, versus the instrument going bonkers. And that becomes very important, especially for our last point, which is that we're operational versus capital costs. Yes, instrument packages and remote instrument packages, autonomous systems tend to be capital intensive. There's no question about it. But what it does give you is relief from operational costs. You've transferred operational costs into capital costs. And frankly, the cost per data point drops dramatically the longer we go through these things. So I think the economics of data collection drive us towards continuous data, remote sense data. But on the other hand, we then need to make sure that we are actually using that data so that we bring that data in and we drive products from it. I think we're still, as a community, growing along that phase. moving from sort of the academic, and I definitely have an academic perspective on this, in which you take an instrument out, you collect data, you come back, and you publish in 2 to 3 years. Well, now the data is online and available, and you can test hypotheses very quickly, and if you've thrown that data open to the world, it's not just you looking at data, it's pretty much anybody looking at that data, and what you will find is that if you put data out, lots of people will start finding it, and they'll start using it, and that's powerful in and of itself. And I think for the most part, what we want as a society to see, we want more monitoring, and we want more eyes looking at the environment and considering the environment that we live in. And I think that's pretty much it. I hope we've left a few minutes for questions here. You're going to take the question?
It's still Julie.
Okay.
Thank you, everyone, for your patience. Today, I found out the reason for our technical difficulties earlier, so that will not happen next week. Please join next week. But right now, we will open it up to the Q&A. Please stay muted, but type your question into the Q&A box on the lower right hand of your screen, of your WebEx. And we do have a couple of minutes to answer any of your questions. So let's see here. Okay, we have, do you know of any instrumentation to measure toxins in situ? Ian.
So there are, that's pretty much an emerging technology. There's the environmental sample ESP, now I'm blanking on what the P is. It's a relatively complex system. It's essentially a lab in the ocean or in the environment in which it can be set up to do many different immunoassays. So they are starting to show up, but it's very early on, and they tend to be very expensive single instruments. But I know NOAA is planning on putting some off in key areas around the United States. There are also other emerging instruments, but as far as I know, the ESP is the only commercially available one.
Okay. We have another question. What about mitigation methods? Is this and we'll cover this in next week's webinar?
We are going to cover the ad hoc mitigation method that we suggested and apparently was taken up by the Army Corps of Engineers in the St. Lucie estuary. But when you think about mitigation efforts, we're really talking about going after the root cause either of the seed population, or we're looking at changing the environment through one of those three considerations: nutrients, sunlight, or time in the environment. And certainly identifying, and we'll talk about this more next week, identifying what the critical path is for the organism to reach a bloom, and then mitigating that particular source. So certainly in the Western Lake Erie, the phosphate impact from agricultural practices is probably the most important one, and they're looking at how to limit that through changing agricultural practices, et cetera. And these are not intractable. They just become a question of leveraging political and economic considerations within the environment. So essentially, the more harmful your bloom, the more support you're going to get with the mitigation strategy. And we'll discuss that somewhat next week. Yep.
Yep. We have a couple questions. Thank you, everyone, for submitting those. Let's see. Since there can be heavy vertical stratification, the live site sensor may not capture the bloom. Other than doubling up the sensors, top and bottom, what other strategies could you advise for fixed installations to sample the entire column?
So there are a couple different ways of doing that. Certainly gliders and autonomous vehicles are one way of doing that, in which you can move through the stratification and get a more complete assemblage of the conditions at any given time. That's one strategy. The other strategy then is to, as you said, add more sensors. But the other one is to simply measure the, get enough instruments out there and measure the vertical changes. So, get a good handle on the physics, measuring the temperature and the wind shear stress, and looking at the flow dynamics using acoustic Dopplers, so that you put the whole thing together. And of course, having, A, I'm a scientist, and B, I work for an instrumentation company, more instruments is always better. More data tends to always be better. You can solve a lot of uncertainties by doing cross-correlation analysis among multiple sites. But these are the type of, real-world questions of evaluating your instrumentation, your packages, and the setup becomes very non-trivial in terms of getting a good data quality out of the installation. You can buy a lot of instruments, but if you don't put them in the water correctly, then you're really not going to get a good value out of that instrument. And for the most part, I'm going to put a plug in here for another hat. For the most part, that is really just handed down among people. I am co-chair of the Observing Systems section for the Marine Technology Society, and we did a special issue of the journal 2 years ago on trading sort of the secrets for how to get good data from ocean observing systems or coastal observing systems or freshwater observing systems, and we're coming out with another one in a couple of months. But that's one in which it is probably underappreciated in the design phase of a monitoring system, but once you start doing it, you start to realize just how critically important it is, and it would be, the more we can trade information on what works in certain situations and not works in others is better. So I think that's a really, really long-winded answer, or maybe not even an answer to the question, but it's a great question. It's really fundamental to a lot of going forward, how we get the best data out of our investments.
Great. Now that we've reached the top of the hour with our difficulties before, we will get back to you on your questions. No worries there. Please, this conversation will continue with part 2, harmful algal blooms, analyzing the data and exploring parameter relationships. But thanks again. I wish everyone a great day. Thank you, Ian, and have a great day.
Thanks a lot, everybody.